Okay. Two times I tried to record this video and it was interrupted by the program. The last time I will try to record it. This video is about earthquake load analysis using mode superposition method. Okay, no problem. First of all, what we do is scaling the modes. Modes are perpendicular to each other with respect to mass and stiffness or rigidity matrix of the structure. So if here n is not equal to r, we obtain 0. If n is equal to r, we obtain a numerical value. And we show this numerical value with capital Mn for nth mode. Here n equals r. And the same result can be obtained if instead of mass matrix, stiffness matrix is used. But after theoretical discussions, people suggested to use mass matrix for scaling of mode-shaped vectors. And they suggested to scale the mode-shaped vectors so that the Mn results in unit 1. Here we have an example. This is the mass matrix of 2-degree freedom structure. These are the mode-shaped vectors. Okay, I will put this document here. Please subscribe to my channel. Continue to recording. Now you see the result is not 1. It's 35 times 0.64. So I divide each term in the mode-shaped vector by the square root of this result. By this way, I obtain the scaled of first mode-shaped vector. Using the similar approach, I scale the second mode-shaped vector. Mode superposition method is very easy. What we do is reading the dimensionless acceleration, floor acceleration values from lateral elastic design spectrums and use this formula. Here, this value is divided by a reduction factor as per Turkish code. You, in your country, maybe you are allowed not to reduce it. Its dimensionless acceleration values do not take into account the g. For example, if you read SAE as 0.2 g, take just 0.2. G is added in the formula here. Take the dimensionless part. Okay. And then this is the open form of this formula. This means that maximum floor accelerations are equal to mode-shaped sum of absolute sum of every mode-shaped vector times g, and this value which is for ith mode taken from elastic design spectrum depending upon the ith natural vibration period. In the example we will understand. But this value is reduced by this formula according to Turkish code. The calculation of this reduction factor is not explained here. It's for Turkish engineers. Instead of this formula, this is the closed form, this open form can be used because summing the absolute values gives me a very conservative value, a very high value of maximum floor acceleration, which results in a very expensive building. Instead, square root of sum of squares can be applied. For velocities, the conservative approach can be used, or square root of sum of squares approach can be used. The difference between two formula is to calculate the velocity. This term is divided by corresponding modes angular natural frequency, as it is done here. Okay. For displacements, we use this formula or this formula. This is the conservative approach. And calculating static and dynamic internal forces. We cannot calculate the earthquake forces act on the masses, floor masses, because here acceleration has two components. One is floor acceleration, one is ground acceleration. We don't know the value of ground acceleration. From the elastic design spectrum, we take the floor accelerations, or floor velocities, or floor displacements. This value is unknown, so we cannot calculate the earthquake load, equivalent earthquake load acting on the floor masses. Instead, what we do is calculating the internal forces in each floor, in each earthquake direction, which gives us the earthquake force acting to the mass. Now, according to Turkish code, structural members, rigidities, bending axial or shear, shall be reduced by means of some coefficients. These are given here. This is for Turkish engineers. Of course, it is conservative not to reduce the rigidities or the stiffnesses. After we have taken the maximum floor displacements and velocities from the elastic design spectrums using stiffness matrix of the structure and the damping matrix of the structure, we calculate the elastic internal forces and damping internal forces, and sum of these two vectors gives me the equivalent earthquake forces acting on each mass, floor mass. Okay, it continues. According to the Turkish code, every floor mass shall be increased, first of all, by means because of live loads, using this formula. This is the live load contribution factor taken from this table. And second, because of that, the earthquake load may eccentrically act on the floor mass. The eccentricity is calculated, and the mass of ith floor is increased for the second time here. This mi is this mi. This mi is the last final value of the mi. Mi is the mass of the ith floor. And then mass matrix is constituted. The motional equation of the structure, motion equations of the structure is written in the matrix form. Then we see the coefficient of the velocity vector gives me the damping matrix. The coefficient of the displacements give me the stiffness matrix. The coefficient of acceleration gives me the mass matrix. We don't know this value. That's why we cannot calculate the right-hand side of the equation. We can calculate the left-hand side of the equation. These shall interchange their places. This is the damping internal forces. This is the elastic internal forces. According to the Turkish law, Turkish code, earthquake code, vertical earthquake forces can be calculated by means of this easy formula. SDS is taken from Turkish codes or AFAD's website. Turkish engineers understand what I mean. This is floor dead load vector. This is a constant value. But using this formula is not recommended. Now we have a numerical example with which we can understand how the mode superposition method is applied. Now we have a three-dimensional, one bay in each direction, two-story structure building. Floors behave as rigid diaphragms, so their bending stiffnesses are infinite. And the lateral displacement stiffness of columns are so much in each direction. The lump masses are so much, but their unincreased values. The damper has a stiffness of 0.05 kilonewton per 1 meter per second velocity. This is where the structure is built. This is the earthquake magnitude. This is the soil type where structure is built. Using these three values, the engineer goes to a website and obtain these two values and obtain these lateral elastic design spectrum, and also these formulas and these values. They are also given in the question. The live load acting on the first and second floor is so much distributed load. Now calculate the lateral earthquake forces using the mode superposition method. And in the first solution, the free body diagrams of each floors are drawn. I explained how these are drawn in another video. Actually, this part is same as the first part is same as the calculation of natural frequency mode shape vectors. And since I have 4 columns, 4 times lateral stiffness value of each column, we have here 0.7 as the reduction of column lateral stiffness, which is taken from here for frame column. Bending stiffness is reduced so much according to the Turkish code. And stiffness times displacement, which occur between the top and the distance after deforming, after earthquake, the distance between top and bottom points of the column is so much. So Fs1, which is the sum of internal forces developed in 4 columns. Fs2 is the sum of internal forces developed in 4 columns, which are in the second story. But the difference between the column top and bottom points is so much because of this explanation. Okay, and the damper forces in each story, in each x and y directions, I have 4 dampers effective. So instead of displacement, maximum displacement, we use for damper to calculate damper forces velocities. C is, as given in the question, 0.05. Okay, then I calculate the increased values of lump masses. I use this formula. I open up this equation to write this equation. Since the floor mass is given to me directly, instead of by dividing the floor weight by gravitational acceleration, floor mass is given to me directly in the question. N is for residence buildings given to me as 0.3. The distributed load is changed to concentrated load. Here 0.3 is taken from here, from this table for residence. The distributed load applies here on the floor, and floor dimensions is 5 meter to 5 meter. So 25 with 25, the distributed load is multiplied to find its concentrated value, the weight, and divided by the gravitational acceleration to convert it to a mass. As a result, I have this much value as a first and second floor masses. And then the eccentricity is here, 5% of this length or this length, they are equal to each other. And then a second increasing of lump masses is done by means of this formula, and the lump masses which I will use in the calculation are so much. Okay, recording continues. Now, first floor motion equation is written using this free body diagram. Second floor motion equation is written using this free body diagram. They are written in the matrix form, as given here. And from this matrix form, the coefficient matrix of acceleration vector is my mass vector. The coefficient of velocity vector is my damping vector. The coefficient of displacement vector is my stiffness vector. So I replace my mass and stiffness vectors here. You know, from my another video, I explained what this formula is. And from here, I derive the angular frequency of 2 modes. and then I calculate the periods of two modes, and then I calculate using this formula the mode shape vectors. I assume phi11 equals 1 meter, and then I calculate phi21, since actually these two equations are same. So I can only obtain the ratio between phi11 and phi21. So 1 meter in the first mode, first floor displacement, and in the opposite direction I have 0.62 meter displacement at the second floor level. Similarly, I obtain the second mode shape vector. But these mode vectors shall be scaled. Using the approach I explained in the beginning, I scale both of them. Okay. Now, free vibration analysis is finished. I can continue with the mode superposition method. These values are given in the question, these equations. The first natural vibration frequency period of the first mode is 1.20. So here in this formula we see 1.20 is between TB and TL. So I use this formula to calculate the unreduced maximum floor acceleration of the first floor. SD1 is also given me in the question. Tn1 is 1.2. I calculate the unreduced maximum floor acceleration for the first floor. Similarly, I calculate the second floor's maximum acceleration. Okay, these are for Turkish engineers. These values are taken from Turkish standards to calculate the reduction factor of maximum floor accelerations. The maximum floor acceleration reduction factors result in 8 for each mode. And then using the reduction factors, I calculate the reduced values of maximum floor accelerations. I replace these values to the equations. Here I open up this term. There are, since my structure is 2 degrees of freedom, there are two terms here. This is the first floor's reduced acceleration, which is 0.025. This is gravitational acceleration. This is the first mode scaled mode shape vector. Similarly, this belongs to the second mode. And using other formulas, I calculate the maximum floor acceleration, velocities, and displacement. Then I employed these formulas to obtain the elastic internal forces in the first floor and in the second floor, and damper internal forces, the forces developed in dampers in the first and second floor. And then I multiply them and obtain these values. This belongs to, this acts to the first floor's mass. So this is wrong. It should be so. This is also wrong. It should be so. Okay. That's the explanation of mode superposition vector. It's very easy. Please subscribe to